How do you do, ladies and gentlemen, and boys and girls, and teachers, and men and women, and people? I am Julius Sumner Miller, and physics is my business, and once more we come to the subject of heat and temperature. And in this lesson, in this lecture, so-called, I address myself to what I have entitled here, The Strange Thermal Behavior of Ice and Water. Very strange. And indeed, it is a marvel to contemplate because the behavior is so anomalous, so strange, so uncommon. Consider the following, which is a little mathematical, but very necessary to our understanding. Supposing I take a glass beaker, just a beaker, and this will not enter our discussion. It is simply to hold what I want to hold. And I put 1 gram of ice in there, one hunk of ice weighing a gram, and I put a thermometer there, and the thermometer reads 0 degrees centigrade. And the stuff is solid. Now, what do I want to do? I want to add some heat energy to there. Now, you know how I add heat energy? I put a candle under there, and I add heat. Now, what happens? As time goes, we see less and less ice and more water. And indeed, after a little time, I don't have a gram of ice, but I have 1 gram of ice water, and what is the temperature of that ice water? 0 degrees centigrade. And how much heat have I added? I have added 80 calories. 80 calories. Now, this should make clear the difference between heat and temperature. I have added 80 calories to a gram of ice, and I get only a gram of ice water with no change in temperature. Now, let me take that gram of ice water at 0 and add some heat to that. Now, what happens? The thermometer goes higher and higher and higher, and pretty soon I have 1 gram of water, and it is now at boiling, so call it 100 degrees centigrade at 1 atmosphere. And how much heat have I added? Well, I have added to the 1 gram of ice water at 0, I have added 100 calories, 1 calorie per gram per degree, so plus 100 calories, and what have I got? I have gotten a gram of water at 100. So you see, here there was a change of state from solid to liquid. No change in temperature. Here there was a change of temperature. Ice, water, water. So change of state requires, enlists, encounters no change in temperature. Now let me add some more heat to this. More heat to this. Now you know what happens. I add more heat to 1 gram of water at 100. There's less and less and less and less and less and less, and pretty soon there's no water. It is all water vapor. All water vapor. Notice V-A-P-O-U-R or P-O-R. So it's all in the gaseous state. And how much did I have to add? I had to add 540 calories to vaporize that 1 gram of water at 100 and make it 1 gram of water vapor. Do you see then the essential properties of this strange stuff? Change of state, no change in temperature, which suggests that to carry, as I put it here, 1 gram of ice from 0 degrees centigrade to a gram of water vapor at 100 requires enormous heat energy, and therefore the liquid state is more energetic than the solid, and the vapor state more energetic than the liquid. Now, let me show you. Here's an illustration of it. Here is a vessel with ice and water, and this is in the hot studio, and the thermometer reads, let me read it. It reads 0 degrees centigrade because it's been here a long time, and it'll read 0 until all the ice is gone. Consider the following. Here is a glass such as you would have on your dining room table with a coaster, which coaster we shall see we don't need, and I am going to fill this right full to the brim with ice and water, right full to the brim. Full, full, full. Well, I can get a little more in there. I can get a little more in there. I don't want it to overflow now. Oh, there it is. Good. Now, is not the ice above the level of the water? Sure it is. Question. As time goes in the studio here, that ice is going to melt. Will the water overflow? No, no. Because, as you know, 1.1 cubic centimeters of ice gives us 1 cubic centimeter of water. That's why an iceberg is mostly below the level of the sea, about 9/10 of it below the level. Another wonderful property. Oh, we've got to get over here. Here's what I'm going to show you. Let us take an enormous cake of ice, big one, and put a wire around it, and put some weights on the wire. Weights. Now you know what will happen. The pressure of the wire being very great, because the area is very small and the load very large, the wire will cut into the ice because it melts it. Now, as the wire cuts into the ice is really melted under the wire. Then the water that results from this melting ice creeps up on top of the wire and freezes again. I'll show you how we do that here, and you can do it for yourself because it's a wonderful thing. Here is the wire put around, and let me turn this around perhaps another way. You can see the two weights here hanging and the wire. And now the wire will embed itself into the cake of ice and take such a shape in turn, in due course, such a shape. And I always ask students, what is the shape of this curve that the wire takes? And I'm going to give you a secret. It is a curve of least energy, and I think it is a catenary, C-A-T-E-N-A-R-Y, which is quite like the curve that the big transmission cables and chains hang in when they hang freely. Now, what's the essential thing to be said? When the water that results from the cutting wire refreezes, the ice is stronger in this place than elsewhere. Is not that an amazing thing? Now, remember, I said that the pressure of the wire melted the ice. What does that remind me of? Have you not made a snowball out of snow, soft and wet, and you squeeze it, and you squeeze it? Yeah, I have some ice here. Squeeze it, squeeze it, squeeze it, and what happens? The snow melts under the pressure. It melts. And then when you let up the pressure, doesn't it freeze? So rather than having a snowball of snow, you've got really an ice ball made of snow that was melted by the pressure and then refroze. Look at here. No water will overflow. But now, much more enchantment in this exercise. I have an after-dinner trick for you. Notice I said trick. I never like to use that word because none of these things are really tricks. They are engagements with nature, and there's no trickery at all. Question. I have here some ice in my drinking glass, and I hand my neighbor at the table, my visitor, a little piece of string about 3 inches or 4 inches long, and I say to him, with such things as are on the table, get out a piece of ice. Get out a piece of ice. Secret. Watch it. I'm going to wet the piece of string, just wet it and lay it on that piece of ice in there, and then I'm going to take the salt cellar and sprinkle some salt on there, and then I'm going to let things rest. I'm going to let things rest a little while. Now what is happening? The salt has depressed the freezing point so that some of the ice is melting. That ice which melts, that is the water from it, now refreezes, and if you will give it your strict attention, I think you will see that the string is fixed to the ice. Watch it, watch it, watch it. There it is. And I say, that is a wonderful thing to contemplate. Indeed, I'm so enchanted by it, I'm going to do it in this big dish, which is filled with ice, and see if I can't lift all of it out. Now, what are we saying here? The strange behavior of ice and water. Now, while that is taking hold of its affairs, you see nature often requires, and nature, remember, When I say nature, we must spell it with a capital N. Nature. Nature sometimes takes a little while for her actions to occur. Let me try this. Watch. I'll let it go a little. But while we're waiting, it should be obvious to all of us that these bits of knowledge which have been gathered up over the centuries have been done, discovered, explored, inquired into, arrived at by strange and uncommon men. And I want to look at some likenesses of some of these, and we should pay them tribute constantly for the great industry that they gave the subject. Let us look here. Ludwig Boltzmann. Boltzmann. Let us look at that man. Incredible. And now I would say to you, should you go to Vienna where he was a professor, there in the quadrangle at the university you see a bust of Boltzmann. And I remember coming upon it and thinking, the man is nearly breathing. It was so alive. Let me try my ice thing. Watch it. Watch it. Watch it. I'm in a little trouble, but there it is. There it is. The ice fixed to the ice because the salt melted some and then the water refroze. Let us take another look here. Sadi Carnot, a young Frenchman, a French engineer, who investigated the properties of heat and temperature, much to his credit and to the credit of France. Or James Watt. Now, we all associate the name James Watt with the steam engine. And what is the story? As a little boy, he saw the kettle on his mother's cook stove popping around, at least the cover of it, and was led to contemplate the consequences of this. Or, here is a wonderful one. James Prescott Joule, whose father was a brewer, and he was led to contemplate some of the properties of heat and temperature, and indeed made a wonderful investigation. He went to the falls in France known as Chamonix with a long thermometer, and there he measured the temperature of the water at the top of the falls and the temperature at the bottom, suggesting the idea that work had been done and the temperature of the water had been raised. And now, for boys and girls everywhere, we must not escape taking a look at young James Clerk Maxwell, the young Scot, whose fondness, let me say, was playing with tops in his later years. So do you see, here was a great intellect whose diversion from his intellectual labors was playing with spinning tops. And I hope you engage in the same, and I shall see you once more.